Hello, and thank you all for coming here today. I'm Shalin, and I'm going to talk a little bit about scaling SolrCloud, but before we do that, I would just want to thank all of you because Solr has tremendous momentum at this time, and it continues to grow further and further. And it's because of you and people like you that it is growing so fast and improving at such a high pace. A lot of regular users, a lot of users search Solr almost every day using different applications, and they don't even know that they are using Solr or anything else. Even developers, sometimes they don't know that they're actually using Solr behind the scenes. And some of the biggest companies in the world use Solr, and I'm very happy that we got a chance to work with Apple and collaborate on making SolrCloud better and better for everyone. The traditional use case with Solr, and I know a lot of you here are actually doing a lot of awesome and crazy things with Solr and SolrCloud, but the fact remains that a lot of people, for the most part, they are actually using Solr with one large index with the same data that is being shared across all the users. And Jessica outlined a case where that's not possible. They have a very different use case. So here, what we're going to talk about is how to actually make Solr work on a use case that it is not really designed for, and what kind of problems we encountered while trying to fix those problems, and how did we solve them. So when we started collaborating on this project with Jessica and her team at Apple, we created a benchmark environment on AWS to test out SolrCloud on a very large scale with a huge number of collections. And we found there were some architectural issues because SolrCloud was not really designed for this use case. So we found those problems and we started fixing them. And along the way, because we were just really pushing the limits of what Solr could do, we found some bugs and we fixed those as well. So here we're going to talk about a few problems that we solved. So problem number one, as Jessica already mentioned, was the cluster state updates and the watchers. So what happens here is that the SolrCloud cluster state is one monolithic JSON, which is actually stored in one zookeeper node. And it is updated whenever a state change happens across the cluster. And all the nodes in the cluster watch this ZK node. And whenever a change happens, they're notified. And then they go to ZK and fetch it again. And it's not just the SolrCloud nodes. It's actually the SolrJ client, the Cloud Solr server, which also watches this node. So you have all the Solr nodes, and then you have all the clients, and you have a lot of people who are watching this node and fetching on each change, right? So if you have 100 nodes, so let's say you have a 100 node cluster and you restart a node. So what happens is you have a watcher being fired on all these 100 nodes, and then immediately they're going to go to ZK and pull out the latest data, right? And it's not just one update, because the node actually goes to the down state, then the recovering state, and then the active state. So just one restart of a node can actually trigger so many things, and this is obviously not scalable as the number of nodes grow more and more. So what we did was we started out by splitting the cluster state. So now what happens is each collection in SolrCloud gets its own cluster state, which is kept in a different ZK node. And now all the nodes in the cluster don't really watch all the cluster states because they don't need to. But what they do is, so let's say I'm a node which has replicas for 2 collections. Then it's quite enough to watch just those 2 collections and not everything else. But what's important is we actually still need to know that a particular collection exists. So we do still keep a list of all the collections in the cluster state cached, but we just don't update it. We don't need to watch it anymore. The reason why we need to do this is, so if you're using the Cloud Solr server, then it's less of a big deal because the Cloud Solr server will route the request directly to the correct nodes. But if you're not using Cloud Solr Server, if you're using a Python or a Ruby or a PHP client, then they will just send requests to any node. And that node should know how to forward this request to the right collection. And for that, it needs to know that such a collection exists in the first place, right? So the clients also don't need to watch all the collections anymore. Instead, what they do is, on demand, they fetch the cluster state for a given collection, and then they just cache it. And when they make a request to a collection, to a particular node, and if that node says that, you guys are sending me a request with a version of ZK that is no longer correct, then it gives a response back to the client, and at that point the client, it would still forward the request though, but then the client can know that, hey, the version that I had cached is no longer valid, and I need to refresh it and get it from ZK again. So this is all open source. This is Solr 5473 and a few other related issues. And this is going to be released with Solr 5.0, which probably should be out maybe next month. The second problem that we found and solved to a large extent, I think there's some work which still needs to be done there, was the problem of the overseer performance. So the overseer is this one single elected node in the cluster which updates the state in ZK. So every time a node changes state, the overseer queue gets an item, gets a message, and then the overseer processes it and updates the ZK server. But then what happens is sometimes the overseer is not able to process things as fast as the messages are coming in. Maybe you're doing a rolling restart, or maybe there's some other problem with the network, or maybe a node was down and due to some bug we just sending too many messages into the queue. That happens sometimes. So when that happens, and it's not just that, sometimes the overseer is just an elected node, right? It also has replicas for different collections and different shards, which means that if that node goes under garbage collection because of high search or indexing load, even then the overseer is not able to process requests for a long time, and it might fall behind. And when that happens, a lot of things go wrong. So a solution to these problems was obviously to make the processing of the overseer faster. So there was a bug where, it was not really a bug, it was just an implementation detail where the overseer would actually wait for a few maybe 1.5 seconds to see if there is something in the queue. So that was not very, that was not a very good way of doing that. So basically we optimized the way it polled for new messages in the overseer queue. The second thing that we did to avoid the garbage collection problem was to have dedicated nodes for the overseer. So with Solr 5476, there is a way to add roles to certain nodes and say, hey, whenever you want to elect an overseer, I want these 2 or 3 nodes to be given preference. That way, what you can do, if you're running things at the scale that Apple does, then what you can actually do is you can have completely separate and independent nodes which do not host any collection at all to be the overseer for all times, And the third thing is the overseer status API. So there was very little visibility into how well the overseer was doing. The overseer status API exposes performance statistics on how well the overseer is performing, how long it is taking to update from ZK, how long it is taking to poll for items from the message queue, and how long it is taking to actually execute each of those update commands. The fourth problem that we had to solve was the asynchronous execution of collection API tasks. So the overseer collection processing was single-threaded, which meant that if you had a long-running split or a create command, then other create commands would not execute in parallel. And there was no, it was basically, so the overseer collection processing was actually designed for very short-running tasks. It was not actually designed for something long-running as a split shard or as a migrate. So we had to fix that limitation, and we did some work which basically made the overseer collection processing asynchronous and also parallel. So now you can pass a parameters which says async is equals to some ID that you give, and then you can just poll for the status of that command using that ID again and again. The third problem was how to actually move data around. So not all users are born equal. As Jessica said, there would be some tenant which has a lot of documents. There would be other tenants with not so many documents. And they wanted to be able to split instead of in the middle at some arbitrary ranges. But at this point, SolrCloud could only split at the half of the hash range only, and not at arbitrary points. And furthermore, there was no way to actually extract a user's data or a tenant's data out to a completely different collection. So we solved these problems by implementing a few enhancements to shard splitting, as well as creating a completely new collection API called migrate. And all of these things work without actually causing any downtime. So now you can actually provide your own hash ranges that you can calculate in your own application, and SolrCloud will actually split at those hash ranges. Furthermore, what you can do is you can just give the prefix of a composite ID, and SolrCloud can extract the data out just for that ID. So you don't even need to give hash ranges if you already have those IDs. So you can just give your tenant's ID the prefix, and it will extract the data out to its own shard. Of course, the migrate API works across collections as well. So if you have a huge tenant, you can just completely move that out to a completely different collection and then scale it separately. And then you can keep on splitting it as the user's or the tenant's data grows. The fourth problem was how to export data. So Lucene and Solr both, they are designed to find the top end matches to the queries, right? So as you go beyond, as you keep on paging through the result set, and as you go deeper and deeper into the page of the results, then Lucene and Solr, they start allocating more and more memory, and eventually things slow down to a crawl, or maybe you run out of memory. So to solve this problem, we implemented distributed deep paging, or what is known as the cursor mark feature in SolrCloud and Solr. So this is a graph which actually shows paging 1,000 documents per page with a 1 million doc collection. And on the bottom, you see the very linear green chart, which is basically the cursor mark feature. And the other one, the red one, is actually the old way of paging through the result set. So if you want to export a huge amount of documents, or maybe all of the result set, then this is the feature to be used. So to actually test all these enhancements, and actually to find some of these problems in the first place, we had to design a benchmarking environment and a test suite which could actually help us be confident about whether SolrCloud can actually scale to that level. So the important point to note here is that we were not actually testing the default way that Solr is used, the one big index which is shared by everybody. Instead, this test was very particular about the kind of problem that we are trying to test, which is having maybe 1,000 or 2,000 collections in one SolrCloud cluster. So we started with very modest performance goals. We had about 6 billion documents. We were trying to reach 4,000 queries per second and 400 updates per second with a 2-second NRT time. And at the start, we were kind of not very sure whether a 2-second NRT turnaround could be achieved, but turns out that we did, and we actually surpassed it, and I'm going to talk about it in a bit. So the traffic distribution was going to be like 80% traffic was going to be served by 20% of the tenants. So obviously there are some large tenants which have a lot more documents and which actually serve a lot more requests. So this is the goals that we started with, and we designed an infrastructure on AWS which would have a separate Zookeeper cluster, a few Solr nodes, separate nodes for JMeter clients, and then some of the support services which would help us manage this cluster, collect the logs, help us visualize it. So we used Logstash, and we used, so this diagram mentions Zabbix, but we ended up not using it because the JMix thing was not actually very useful for us at that time. We started out with Kafka, but we kind of figured that it is probably overkill for these kind of use cases, so we ended up going with RabbitMQ. But we might actually try Kafka again because RabbitMQ was it did not work quite well for us. The logging was, of course, it was collected using Logstash, and also each host also had collect daemons running. So we were actually collecting stats from everything that is given out by VM stats. The machines had some small cores, some medium cores, and some large cores, but not all of them did. And in fact, the numbers that I'm going to share is going to talk only about the small cores. We use the i4 X large instances on AWS to run all of these tests with dedicated IOPS. But before we could do that, there were a few other problems which had to be solved. Namely, how do we actually manage such a large SolrCloud cluster in the first place? So until this time, I'm sure a lot of you deploy Solr and SolrCloud on AWS, and a lot of you have written your own tooling to actually manage these kind of clusters, but there was nothing available in open source which we could use directly. So Tim Potter wrote the Solr Scale toolkit, which is now available as open source, and it can be used to stand up SolrCloud clusters on AWS and manage them. So you can, it's a fabric-based script, it's a Python-based script, which you can say, hey, I want a new ZK ensemble with 5 nodes. I want a new SolrCloud cluster which talks to this ZK ensemble, and I want to have these many nodes and this collection and these many shards and so on and so forth. What it also allows us to do is that because we were going to run these load tests over and over again, and we actually did not want it, like every hour that you spend on AWS costs money, so we did not want it to create clusters from scratch, index all the data, and then start testing the querying and updates on an existing collection. So the Solr Scale toolkit has support for backing up collections and cloning them from S3. So what it does is we would stand up a cluster, we would have our own load generators which would write data to the SolrCloud cluster, and then we would back it up on S3. And then whenever we needed to run some of these performance tests, we would just clone them back from S3 and start using them. So this is all open source and it's pretty good. If you have not tried the Solr Scale toolkit, I ask you that you actually give it a look. It's pretty good, works great. Lucidworks Silk, the Solr plus Logstash plus Banana, the Kibana port, was used to collect the metrics, collect the daemons were installed on each of these hosts. RabbitMQ was used to queue messages before they were delivered to Logstash. As I said, we initially started with Kafka, but we discarded thinking that it might be overkill. But we are not quite happy with RabbitMQ. It had problems with, crashing randomly and restarts, and we might actually go back to Kafka when we need to do this again. To generate load, we wrote our own randomized data generator. So how it would work is you would give it initial seed value, and then it would generate more random numbers. And using those random numbers, we would generate, so basically each document gets its own random number, and then that random number is used to generate the fields for those documents. And this is important because we want to regenerate the whole data set whenever we need, and also we need to generate queries which are sure to hit some documents. So it was useful to be able to generate all the fields using a random value. Okay. So JMeter was used to generate the load, and we basically used the Java action sampler in JMeter, which allows you to write arbitrary Java code. And what we did was we actually so just sending an HTTP request randomly from JMeter is not useful to test performance for SolrCloud, at least in this and many other cases, because if you are actually using Java, then you would most likely be using the Cloud Solr server, and that guy routes the request intelligently to the leader. So for example, if you're sending an update, it would route that update to the correct leader. And that's not going to happen if you're just using JMeter. What would happen is the JMeter would just send it to some random node, and that guy will determine that, hey, this request actually needs to go to that leader over there, and it would forward the request. So in many cases, it would just add an extra hop and screw the results. and that would not be directly comparable with what you would get with the Cloud Solar Server. So it was very important for us to actually embed Cloud Solar Server right inside JMeter, and we did that using the Java Action Sampler. We first tried the JMeter distributed mode, but that itself became a bottleneck when we started pushing the limits, because the JMeter nodes would chat with each other a lot, and that itself would become a bottleneck. So we were not able to go beyond a certain load when we were using distributed JMeter architecture. So what we ended up doing was to just have completely independent JMeter clients running on separate nodes, and we would just start all of them together using a script. This isn't open source yet, but we are working on it, and hopefully we'll have something which can be used by anyone to generate random loads and to test this out. So this is one of the results that we got from our performance tests. So this test was run on 30 boxes running on AWS with 120 JVM, 120 different Solr nodes, and 1,000 collections, a little more than 6 billion documents. And the results were actually pretty good. Like, we really needed just 4,000. We started thinking that maybe if we can reach 4,000 it would be great, but we actually, once we had ironed out all these problems that we detailed, we found the performance to be quite good. It was about 15,000 queries per second and 2,000 approximately writes per second. And this test, so a lot of these tests were run for 24 hours continuously, because we did not want to find the peak performance. We actually wanted to see if we can actually sustain this performance over a long time. So we had these 24-hour tests, and we were actually able to see sustained performance of 2-second turnarounds on updates and with these numbers. So this was pretty good. This was almost 3 times the numbers that we wanted to have. So we sadly had to stop testing at that point. And our biggest cluster cost just $120 an hour, and I think this is great. AWS is so great, because we don't have to buy so many servers to test this out. We could just rent them out and just give them back. So yeah, this was great, and it's not over yet, because we continue to do this continuously, at Lucidworks, and I'm sure a lot of you are pushing the limits as well. And what we're doing is, we already have most of this infrastructure to run these tests, and we continue to run them. And I think Tim recently published an indexing benchmark on the Lucidworks blog, and we are, running these tests, and we're trying to find numbers for queries, and also not just for this use case, but other use cases as well. But that is a completely different talk, and we probably will publish something quite soon. So, yeah, Jepsen. How many of you have heard of Jepsen? Okay, some of you have. So Jepsen is a tool which helps you test your data store against network partitions. And for the last 1.5 months, we have been running Jepsen against SolrCloud. And we have not found any catastrophic bugs, but we have found a few implementation issues, and we have kind of been fixing them. Most of those have already been out in 4.10.2. And obviously, this is a process which does not end once you have run it and fixed it. It's a continuous thing. So we are setting up an internal Jenkins which would run Jepsen against every revision that is committed inside Solr and SolrCloud. And we'll continue to improve this as we go on. But that's a completely separate talk and a completely different blog, and you will see some details coming out very soon. And it's not just us, right? It's all of you. This is just one company which is using Solr and SolrCloud at very large scale. But there are so many of you who are doing that. And it's because of people like you that we continue to push the limits, and we keep on improving Solr from where it is and into the future. So some of these issues that we are still working on, and not just us, there are other people in the community who are working on this as well. The Solr 6220 is a replica placement strategy. So once that is in, you will have the flexibility to locate the Solr nodes in a DC data center awareness fashion or a rack awareness fashion, or if you're in AWS in, within the same availability zone or across availability zones, whichever way you please. There is the cross data center replication. A lot of work is being done there by the community, and we're really excited because it's a feature that a lot of people need, and Apple also needs this. Mark Miller recently committed this, the auto-add replicas on HDFS. So if you're using HDFS, then if your replica goes down, your index is still available on HDFS, and you can just immediately stand up another replica pointing to that location. You don't actually have to wait for that replica to recover and catch up because the data is already there. Solr 5986 allows you to kill queries which are taking a long time enumerating through the terms. So if you have complex queries which have to go through a lot of terms, you can provide a time allowed parameter, and it would stop the processing if it goes beyond that time. And that helps you, stop runaway queries. And then there is Solr 5750, which is a backup restore API. So we're doing there is a way to backup, but that is only on a single node. There's no SolrCloud level backup available yet, and this issue is tracking developing such a feature. And obviously, there are so many things that are being done in SolrCloud. It's just not possible to cover all of them, in this presentation or in this slide or even 10 slides. But the fact is that SolrCloud continues to get better and better with each release, and we're already at a very good level right now. So thank you all, and I'm very thankful to Apple for helping, collaborating with us to improve SolrCloud, not just for them but for everybody. And I'm very thankful to all of you who are here to make Lucid Revolution such an awesome conference. Thank you, guys.